What do you know about train derailment? You might have seen it in a movie, but it is a real problem in the world today. While derailments can be the result of high speeds or human error, the plurality of derailments are due to problems with the track. Every year in the US, over 1,500 derailments are due to common track problems like worn rails, cracks, engine burn, and gauge deviation. Fortunately, there are professional inspectors who work to find these problems before they cause a derailment.
There have even been high-tech inspection vehicles that can inspect the rails quickly and accurately. But these vehicles are very large, expensive for railroad companies to rent, and they have to pay a trade professional to operate them. Small railroad companies like Shenandoah Valley Railroad that own a lower mileage of track can't afford these inspection vehicles, so they have to rely on manual visual inspections alone. This is where we hope to make an impact.
We want to help railroad companies prevent derailments by providing an affordable alternative to these high-tech inspection vehicles that can also be flexible in their deployment and operating cost. Solution space, envisioning our design. We started off first by coming up with a mind map for all the different concepts available in our design space. The different aspects of that mind map were then used to create different combinations of feasible designs on a separate glass board. Developing design combinations. We then took those design concepts and put them through pass-fail feasibility tests. Before moving forward, we then needed to decide which type of defect we would focus on, and in this case we focus on defects of the surface of the rail, including wheel burn surface defects, as well as rail gap and cracking surface defects. A functional model on data collection was then developed according to surface level defects, including actuating electrical energy, capturing visual data, as well as processing that data. A second functional model focused on mobility was then created, following key aspects such as distributing electrical energy, distributing signals, as well as transferring energy to be translational. Object detection, detecting surface level defects on rails. Object detection uses a camera to visually detect an object while then identifying it using machine learning. Of course, in this case, this is a crown. But for our purpose, we need to do this with a rail. So this involves taking many pictures of rails and identifying them in a label image, such as this, through RoboFlow. This is an example of a good rail label. This next image is an example of a bad rail label, where we have the entire rail highlighted as a bad rail to signify the area around it isn't acceptable, as well as the specific spot, which is a wheel burn in this situation. We then take these labeled images and put them through what is called a label map. This label map is then fed to whatever machine learning you have for object detection. In our case, we tried using Anaconda initially, but we ran into many issues with backwards compatibility between TensorFlow 2 and TensorFlow 1. After a few weeks of bug fixing within the Anaconda prompt and TensorFlow, we eventually switched over to RoboFlow, which is an all-in-one API for faster RCNN and TensorFlow record generation. We were able to upload all of our images into this library and sort them into train, validate, and test groups. Once your image library has been built and your TF records have been generated, you can push it through and train your model in faster RCNN through their pipeline. Here is an example of the background architecture happening within the model training process. Thankfully, Google Colab offers GPU-based model training for object detection. The outputted inference graph can then be deployed out to a Raspberry Pi running Keras. Physical design, concept embodiment. A CAD model was developed of our design in SolidWorks. This includes our metal frame, camera mounts, axles, and wheels. FE analysis was then conducted on this within SolidWorks Suite. This would help us determine if our design would be able to hold more than enough weight to overcome a factor of safety much higher than our current design. This was then backed up later with hand calculations done using structural analysis techniques. Gearbox calculations were done using ratios of gears to determine if they would be able to push the weight given our motor's specifications. The first proof of concept wooden frame was then developed using plywood and scrap wood from the Fab Lab at JMU. This was then used to determine actual compatibility with other components, such as our camera mount seen in this image. This was able to clamp on correctly without damaging the wood frame. We then mounted the bearing housings at the end of the wood frame pieces and fit the axles and the wheels to determine if it could hold that weight and support the design as it rolled down the pair of tracks that you see here. Metal frame, periphery design, and attachments. New aluminum bearing housings were purchased since we were unable to manufacture our own housings due to the dangers of welding aluminum and damaging the interior bearing. This process was complete and mounted as we then press fit the aluminum axles through them to begin conducting tests to make sure that this functioned as optimally as our previous design with our wooden housings on our wooden structure frame. This test is shown here. The next step was rethinking the way we were going to be mounting our gearboxes to the metal frame. There were multiple iterations. Here shown is the first one with a foam support underneath the motors. The second iteration involved two vertical supports, however, we did not have enough 80/20 material to support this endeavor. We later then shifted to a double 80/20 on the bottom half of the gearbox shown here, supported on either side by the center two bars of the H. This is a test run on that design. This is the first time we ran multi-speed control commands through our motor controllers. As we can see, the motors reverse polarity. The 3D printed camera mount was then adapted to make sure it could fit onto the 80/20 frame outside of where the gearbox output shaft would be. Most of the previous concept embodiment work that was done in lab was done within COVID-19 restrictions as seen in this photograph. As you can see, the workbench got pretty crowded with all the different things we were working on. We later were able to test out the design with all electronics on the mock rails. Here is the most up-to-date look at our design. Currently the axles are being cut in this shot so that they'd be at shorter length and have less weight on the design. However, all the electronics are mounted and the motors are connected. Future work. We are continuing to test and evaluate different aspects of our design. Included is this video clip where we finally corrected different flashing codes of our motor controllers back to green flashing. They also operate all at the same time in this video, showing both operating at constant velocity through code. We have already made several adjustments due to these tests, such as in this first clip where we noticed wheel spin on startup. This was tuned out in new code shown in this clip where we had a slow start and no wheel spin. We invite you to stop by our Saturday exchange session to talk more about our testing at Shenandoah Valley Railroad. Support the team, fill out our survey, and watch our previous episodes. The first two episodes of our Capstone video project are available on YouTube at these two QR codes. The support survey and Google form can be found at this QR code. A very special thank you to Shenandoah Valley Railroad for lending us two pieces of their rail for us to test and utilize in our training, and for allowing us to take a couple thousand images of their rail on their property alongside one of their own manual inspectors guiding us in order to help develop our object detection library. One final thank you to our Capstone advisor, Dr. Jacqueline Noggle, who has supported us over the past 2 years.